Let's start with this guy. Do you know who is he? Anyone? Ah, not exactly. It's Mark Zuckerberg. He is known in the web world for the one sentence he said back in 2012 about their mistake as Facebook that they made, that they invested in the web platform too much, and that they should instead invest in native platforms back then because their results would be better. It was in 2012, so there were times when we had no progressive web apps, we had no push notifications in the web, we even had no camera access APIs in the browsers. But the one thing he mentions the most time was very simple, and it was performance. The team at Facebook tried to fix the problems they have, but they found no way to work around it. They left the web platform, leaving the message that the web is just too slow for the real life scenarios like their web app. And we still hear the echo of this message even today. Before we go further, let me clarify one word in the title of this talk. I have a mobile word there. But reality is, right now, the statistics are pretty clear that the traffic from the mobile devices already surpassed the traffic from the desktop devices. And right now in Poland, it is more than 60% of the traffic that originates from tablets and mobile phones. So can we still talk about the mobile web as something distinct, something different than the ordinary web, the real web? I don't think so. So we can probably cross out the mobile word and the whole talk will be still relevant because the rules are pretty much the same. We just need to focus, move the focus from that kind of environments that are highly connected, very powerful, that we as a developers are probably used to, and instead think in terms of that kind of devices that resembles our real users much more. And this is probably some kind of middle-end device from 2015 or something. That means that we need to test our applications on that kind of devices. Otherwise, we are probably missing some performance bottlenecks that our real users has. And we are producing the web that is slow by default, that is guaranteed that it cannot compete with native apps in terms of performance. Coming back to the title of this talk once again, what that Holy Grail actually is. In medieval mythology, it was something that everyone wanted to have, but no one actually knew how to find it. No one actually knew how to reach it. And I think the performance in the mobile world is something similar like that Grail. Because everyone heard that kind of statistics, like it's very important to have a website that loads quickly because the conversion rates are the best when the website's loaded fast enough, and the opposite, that the bounce rates goes up if the website failed to load quickly enough. So being in that sweet spot over here should be our Grail, should be something we should look for. But there are actually many ways that might lead to that Grail. Performance starts at the backend, at the server-side throughput. If our backend is slow, we cannot probably fix it much on the front end. Then we have network. Network might add a lot of overhead, a lot of time spent on latencies and the routing. Then the content reaches the browser, and browser needs to process everything, needs to run the JavaScript, needs to render everything. That can take time. Then, after this is done, we have animations, we have interactions. All that needs to be smooth. We need to provide a user experience that is fast enough. And even UX can be treated as a part of performance because we have some patterns, like, for example, optimistic UI, where we can a bit lie to our users that actions that he made were immediate, and instead do the work in the background, and only in case of the error, roll back the action and show the error message. We are not going to talk about the server side, and we are not going to talk about the UX. We will focus on the three things that matters most for the front-end developers. I assume most of us here are probably that kind of persons. So we have a network part, a load and render part, and the runtime part. As we go, I would like to show you my path with the website I am running, what web can do today. Anyone already heard about it? That is nice. This is a website about the capabilities of the web platform, especially focused on the mobile devices and on the hardware we have in our mobile phones, and about the integration of the web applications into the mobile operating systems. I am running this as a side project after my kids go to sleep, so I don't have much time, and I'm not investing a lot of time in it. So initially, I didn't care at all about the performance. So I've thrown everything that was the easiest into. The result was that on a simulated slow 3G connection from the mobile phone, the page took 7 seconds for first paint. FP is first paint, so it's the first moment the browser actually shows something to the user. Before that 7 seconds, there was a blank page. And it took almost 10 seconds for first meaningful paint. FMP is first meaningful paint, so it's the first moment that the browser shows something of a value to the user, and in my case, these are the labels for the features that user can interact with. So definitely there was a room for improvement in my website. I would like you to show what I did and what were my results in terms of the loading time. Okay, let's start with the first part, and this is networking. HTTP2. Who is already using HTTP2 in their projects? Well, not many, and this is pretty consistent with the statistics that tells that only 16% of websites are using HTTP2 at the moment. And this is bad, because just by enabling this newer version of a protocol, we can have a lot of gains at the performance front because of the header compression, and especially because of the better connections multiplexing that HTTP2 provides. I will show you a demo that is kind of interesting in that topic. These are two images being loaded in the same way from the same server. Both of these images were loaded from the parts. Each tile was loaded in a separate request. Obviously, the left one was loaded using HTTP 1.1, and the right one was using HTTP 2. Here, the difference was 5 times faster using HTTP 2. This is interesting, but obviously, the real-life scenario isn't that glorious. In my case, my website wasn't made of jigsaw puzzles, so I was able to shave off 3% of my load time, but still it was quite easy for me to enable it, so why not? It's still a benefit. And with HTTP2, there comes yet another potential benefit with server push functionality. So if we have a server that is push capable, and if the client, the browser site, is push capable, when the client is asking for some resource like index.html, the server might respond with not only the data that was requested, but also to push the things that the server knows the client will probably require quite soon, so JavaScript or CSS for our website. So that might lead us to quite good results soon. The problem is it is quite complex to implement on the server side, and it is not yet consistently handled within all browsers. So we might look for an easier and cheaper alternatives. And we have these as preload and prefetch. Preload is actually a very simple thing. It's a link element that we can add to our head section in HTML that asks the browser to download something as soon as possible, even if it's not directly used by the page yet. It is especially useful, for example, for web fonts that are normally only discovered quite late in the process when the CSS is being parsed. So the fonts are downloaded quite late, and is kind of a crucial thing for our website to have the fonts downloaded. And prefetch is similar. It is for navigation. So if we have some kind of stepped process or kind of a wizard, and we can guess where the user will navigate next, we can ask the browser to prefetch the HTML and the resources needed to show the next page up front. So when the user actually requests it, it is already in the local cache of the browser. I use preload for my website. I have 2 fonts there. One is for icons, the second one is for text. And just by adding those 2 lines in HTML, by preloading the fonts that I'm using, my first meaningful paint time decreased by 1.5 seconds. So it was amazing. For 2 lines in HTML, I was able to have that much improvement. There are other kinds of prefetch available in some circumstances. Like if we are talking a lot with an external domain, if there a resource that is placed on external domain, we might ask for DNS prefetch so that our first request does not pay the cost of DNS resolving. We can even establish a TCP connection up front if that makes sense for us. Or in some cases, in some browsers, we can even ask for pre-rendering. So it is a kind of a hidden tab that the browser opens, renders the whole next page within that hidden tab, and when the user actually requests it, it's just swapped into the view, so it's immediate for the user. Content delivery networks, CDNs, are still a very important thing in our delivery. This is a typical breakdown of application times of parts of the requests taken from Chrome DevTools. So it's not the content download that takes the most time in our typical front-end application. It's waiting, time to first byte, TTFB, it's time to first byte. It consists of server-side processing, but in case of front-end application, in most cases, that doesn't matter that much because it's probably just a static JavaScript or CSS. So it's the networking part that matters mostly here. We have all the DNS stuff here. We have TCP connection. We have TLS negotiation, all the routing stuff. And what CDN offers us is to place the content as close to the user as possible, cache the content within their geographically located in multiple locations nodes, so that when the user requests it, the routing time might be reduced as much as possible. So if we happen to have a distributed user base or our hosting is far from our user base, we can have an improvement by an order of magnitude for routing part. Old and basic techniques are still very important, like plain old HTTP cache header, cache control. We should always serve our immutable content with long expiration dates so that in subsequent visits, our users are not even touching the network to get the data. And all the mutable content should be marked with cache control no cache, which literally doesn't mean literally not to cache. It means that the browser will will cache the content and ask the next time if the content the browser has is still valid to be used in that request. So we might save something on the transfer time too. And we can go further right now with service workers. Service workers allows us to cache things needed to render our website up front. So if we have our service worker working in a cache first manner, we can avoid going to network at all, providing an offline experience, for example, for our users. And in terms of caching, it's the same. We have everything in place, so there might be no network involved. What were my results? With cache headers, a subsequent visit, the rendering on a subsequent visit took less than 3 seconds. And with service worker, it was less than a second. So there was no network involved, or only a single request was involved, so definitely our loyal users will benefit from that kind of optimizations. But we obviously still need to optimize the general scenario of the first load because it's valid only for subsequent visits. And here we have the critical rendering path in the load and render part that helps us the most. So critical rendering path is an order in which the browser processes the things being downloaded. And in most cases, it is drawn in that kind of waterfall chart. You might be familiar with it from Chrome DevTools or websites like webpagetest.org that shows the download in the same format. So let's think about the processes that the browser needs to run in order to present the user with the website. First, rendering. So the process of putting stuff on the screen. How do you think? When can it happen? Can it happen all the time during our process? Well, no. It can only happen until the first CSS is discovered. Then it needs to stop and can be only resumed after that CSS is downloaded and applied. Observation number 1, CSS blocks rendering. Why is that? It is because the browser saves on repainting the whole website, because it's pretty obvious that the CSS that is in flight will affect the layout in most cases. So it just waits until it knows what should be rendered, and the rendering is then stopped. Now let's think about scripts. When JavaScript can be executed in that process? Can it be executed immediately after it was downloaded? No, it needs to wait for the CSS too. That might be surprising, and that means that CSS is kind of important in the load and render process. Yes, it is. Observation number 2, CSS blocks script execution. Why is that? This is because our scripts might ask the DOM for the computed styles for each element, and in order for the browser to respond deterministically, it needs to have that CSS available. So if the browser knows that CSS is in flight, it needs to wait for it to be available. Now let's go one level deeper into the most basic process that our browsers do when the page is being rendered. So parsing. So the process of translating the incoming HTML stream into a DOM tree. That sounds like a pretty basic thing, and that should not be interrupted with anything, right? No way. It is interrupted with the first JavaScript that is encountered. And then the parsing needs to stop. Nothing can be parsed. No DOM tree can be built up until that JavaScript was executed. So it's a pretty large gap over here that no further parsing can happen. Observation number 3, JavaScript download blocks parsing. Why is that? It is because we have legacy APIs like document.write available in the browser that are intended to modify the DOM tree being built exactly in the place and in the time it was encountered. So the browser have no way to know if we are going to use document.write and needs to check it first, obviously. So it needs to wait until that script is actually readable for the browser. Can we do something with it? Yes, we can. We can mark the script as asynchronous. So we are telling the browser it can proceed with parsing. We are not going to shoot in our foot with document.write anyway. So move on and don't stop the parsing. It is very simple. It is just an async attribute that we can add to the script element. But we still have a gap here for execution. Execution blocks parsing, observation number 4. Why is that? It is generally how JavaScript works. JavaScript tends to work in main thread in the browser, and this is the same thread that is used for parsing. So they need to share the same thread by default, and the parsing needs to stop for JavaScript execution, unless we mark it as deferred. In case we are not actually interested in having that script run as soon as possible, for example, for social widgets, ads, or any other thing that should not block our basic processes for loading the website, we should allow it to be deferred. It means that it would be run after the parsing is actually completed. So it will still be blocking, but it will block nothing because the parsing is completed, and the user will probably not be affected by that execution. Okay, now I will show you videos that I've borrowed from Google I/O talk from this year, from performance metrics talk. And it will show a website being loaded in 2 different modes. Sorry, this is how we have our scripts deferred, just by adding a single attribute again. And these are the 2 modes. The left one, on the left one we have the header, we have the loading indicator, and something is working immediately for the user. And the right one was a bit faster, but initially it was blank. And how do you think, which of these variants people tend to like more? The faster one or the left one? The left one, because it immediately have shown something to the user, giving them an impression that the website is already running and working hard for them. And the right one looked like broken until it was done. So they might abandon if the loading time is too large. So we can actually try to have that left experience. How can we do that? We can inline the CSS that is needed to render that part of HTML that should be displayed as fast as possible. So it might only be a header and a loading indicator, for example. That should be inlined in a style element on the top of our HTML structure. Then we need to make use of the streaming of HTML so that we are not blocking the parser and rendering in any way. So we should have no blocking JavaScript or no CSS served on the top, so that these elements might be drawn to the user. And all the rest needs to be deferred, needs to be pushed and loaded dynamically at the bottom in most cases. That might not be trivial, especially for existing websites. And that might be a costly thing to implement this way. but it's, the perceived performance for the user will increase dramatically in this case. What is also important, and probably more even important, is the size. On average, in 2017, the websites to fully load needs 3 megabytes in the size of the requests, and half megabyte in each are the JavaScripts. So we have a website obesity crisis. This is a title of a great talk by Maciej Cegłowski. I really recommend you to watch it later. All the links will be available later, so don't bother right now. It's a real eye-opener. There is another website called Cost of Modules that summarizes what is the impact of adding a module into our bundle. So for example, if we add a full Lodash package that is quite popular, we are adding half a second to the download time over 3G. For jQuery, it is 0.6 seconds, and for React DOM, which is a bigger part of React, it's 3/4 of a second. And I'm not saying that libraries and frameworks should not be used at all, but we should always remember that there's a cost in everything we are adding to our front-end application. And in case of JavaScript, it's not only the loading time, but it's also the time to parse the code, to compile it, and to execute it. And that might sound like not much, but for example, React on iPhone 5S. React is a relatively lightweight framework, and iPhone 5S is a relatively powerful device. It still takes more than 100 milliseconds just to complete that yellow phase. So it's a big problem for larger libraries or for lower-end devices, and we need to remember about it. I had the same problem on what web can do. I have run a tool that is available bundled within the Chrome DevTools called Coverage. And that is a great tool that highlights all the code I am using and all the code I am not using, and giving a percentage of what is used and what not. And it turned out that I am using Bootstrap, but only 5% of the Bootstrap code I am shipping. So 95% of that code was totally useless. The same with my JavaScripts. Half of them were not even run in my website. There is a page, whatdoesmysitecost.com, that translates that into an actual value in monetary value that our users pay in their data plans to download our website. So it's not only affecting the load time. Serving the useless code is also kind of offending to our users, that we are asking them to pay for something we are not going to use at all. So what can we do? We can tree shake. Tree shaking is a technique that is available in most of the modern bundlers. And it's an automatic way to remove the dependencies we are not using, we are not referencing from other parts of the projects. We can code split. Instead of serving a single bundle of JavaScript that consists everything we can possibly use, we should split our code into smaller chunks, maybe one per view or one per component, and load it on demand. Especially when we are using HTTP2, it's not that bad at all at the moment. But nothing is more important than the third point. We should apply critical thinking and common sense to whatever we do, because it's most probable that we don't actually need everything in. We can remove some of the code we are shipping without affecting our functionality or our appearance at all. That was exactly what I did. My website is relatively small, so the numbers maybe are not that bad, but still, I was serving more than 40 kilobytes of CSS and almost 150 kilobytes of JavaScript, and I have spent like 2 evenings removing all the code that it was easy to remove and that I was not actually using. And I was able to remove 3/4 of my CSS and half of JavaScript like this, without any effect on the functionality and appearance of the website. What was the result in terms of the load time? It was amazing. It actually made it 26% faster, and this is the biggest improvement I have made. Definitely not something to be missed. Last but not least, images. Images are a significant part of our average website size. it is marked in the blue on that breakdown. So this is definitely something we should optimize. And there are two rules. First is that we should always remember to serve images in a correct format. So especially if we have some kind of charts or other vector, possibly vector images, they should be always served as vector images. In most cases, SVG would be far more optimal than serving it as actual image. And if we are actually serving images, they should be compressed enough. And the second thing is that when most of our users are on mobile, we should not serve them 5 megabytes images because it just makes no sense for them. And they will just not use it. We should either use src set attribute or picture element to serve our images in a responsive manner. Okay, now a third part about runtime. And similarly, like we had a critical rendering path that we needed to understand in order to optimize it in the load and render part, here we have a pixel pipeline. So this is the list of things that the browser needs to do in order to render a single frame for the user, a single piece of visual information. It all starts with JavaScript or HTML and defining a change, something to happen on in the DOM structure. Then, when the styles have changed, all the styles needs to be recalculated. All the affected styles needs to be recalculated. It means that for each DOM element, the set of rules needs to be found out with all the specificity rules applied, with all the inheritance applied. Then the browser can go to a layout phase. Layout phase is about the geometry. So the browser calculates for each element affected where on the screen it should be drawn and what are the widths, heights, and margins, and all the dimension-related stuff. Only then the browser can put the elements into visual layers, and each visual layer is pixels for each particular visual layer are calculated. So it is filled with actual pixels that will be shown to the user. And finally, all these visual layers are squashed together into a single frame that is presented to the user. This is in most cases delegated to the GPU, so it's pretty fast. Talking about frames, it is pretty well known that we should target to have 60 frames per second in order to have the smooth interactions and animations. And that means that we have a tight window for each frame that is about 16 milliseconds, so it's a really tight one. So how can we fit everything into a 16 millisecond time window? Well, it's very hard. And in case of a complex website, the non-trivial CSS change will most probably cause a style recalculation that takes more than 100 milliseconds. So it's very hard to keep that stuff small. But there are some tips. The most useful one is just to be lazy. We should avoid as much work as possible. We should just do less. And this is generally a good life hack anyway, right? There is a great website called csstriggers.com that lists some CSS properties and what the browser needs to do when we change that property for a given element. So, for example, if we change height or left, or it's the same with width or height or margins or any other CSS property that affects sizing, nothing can be optimized. The browser needs to repeat the style recalculation, layout phase, paint phase, and composition. So all the elements needs to be applied within that single frame. But for example, if we change a background color, some browsers are smart enough to figure out that it has no way to impact the sizes, the geometry, because changing a background will not resize the element in any way. So they skip the layout phase and go directly to paint. So we have one phase out. That's good. And with transforms, we can do even better. Because if the element is on a separate visual layer, the transformation like rotation or scaling can be delegated to the GPU and be calculated as a kind of matrix transformation only. So the browser can skip both the layout and paint phase. And it's the same with opacities. The opacities is a matrices maths only. can be done on the GPU level only. So how do you think? Which of these properties are the best to be used within our animations? Obviously, the ones that are the easiest to apply. So the good thing is that we can map most of or all of our traditional position-based animations into transforms. Transforms are a very powerful thing that are purely CSS based. We can apply some maths and instead of modifying sizes of elements, instead make transformations on these elements. One important thing to note here is about the visual layers that I've mentioned several times. Browsers need to optimize the memory usage too. So in most cases, the elements will not get its own visual layer by default. In fact, the browsers will put all elements into a single visual layer if possible. So it means that if we are starting to animate an element that is not on its own visual layer, the browser needs to pull the element off that visual layer first, and we are losing all the possible optimization, and this is suboptimal. Unless we mark it as will change transform in CSS, and it instructs the browser that we are going to animate that element, and it should be put into a separate visual layer upfront. Now, scrolling. Scrolling is hard, full stop. And even the libraries that intend to use it correctly have some problems with that. That was an example of an animation that was recorded on a desktop device. It was smooth, it was okay. Now let's see how it looked on Samsung S8, which is kind of a high-end phone. Here is the stick. So it is not smooth at all. Why is that? The reason is pretty apparent if you think back about the pixel pipeline. It's just not possible to fit that much things in a single frame. So it's just 16 milliseconds. So how can we deal with that? What's the optimization here? Unfortunately, we can't do much here. It's just a matter of compromise. Either we are running an expensive scroll event handler and calculate and change everything and trigger all the pixel pipeline in each single frame and have the fancy parallax effects, or we have a smooth user experience on the lower-end devices. We just have to choose. Because scroll events are, the handlers for scroll events are run for every single frame. And if we are actually doing something there, we need to remember about that pixel pipeline. It's even worse with the underlying events that might cause scrolling, like wheel events and touch events. These events are able to cancel the scrolling at all. So whenever we have a handler attached to wheel event or touch start event, the browser needs to stop the scrolling for the period of running that event handler to see if we have called prevent default on that event so that it needs to figure out if the scrolling can happen or not. This one, at least, we can optimize out with having our listener registered as passive. So it means it tells the browser we are not going to cancel the scrolling. It can proceed, and we are giving the browser a bit bigger room to breathe in that tight window. Two more goodies about per frame rendering. Request animation frame is a thing in DOM API that's available in DOM API. And this is about running a code once per frame. By passing a callback to request animation frame, we are ensuring that that callback will be called exactly once in the next frame, so that it's a way to save work in case we are collecting some data or changing some data in each frame. We should avoid running it unnecessarily, so by wrapping it into a request animation frame, we have that guarantee from the browser. The second one is request idle callback. That is useful if we have a JavaScript that executes longer than 16 milliseconds, and it is a kind of common thing to have. So if we pass it as a function to request idle callback method that is also provided within the DOM API, we are asking the browser not to run it immediately, but wait until nothing is happening. So no animations is in progress, no animation is in progress, and no user interaction like scrolling is in progress. So we are trying to avoid affecting what our user actually sees. Okay, I am aware that there were many tips today in this presentation. So instead of doing a full recap, let me just give you 3 takeaways that you should be able to apply to your job on Monday. First is to prioritize performance. There should be no reason for websites to be necessarily slower than the native apps if we invest the same amount of time into thinking about performance. If we test on real devices, because in the case of mobile applications, it is pretty obvious that they will work on mobile devices, and in mobile development, they are always testing on the real devices, and in the web world, it's not that obvious. So if we prioritize the fact and treat performance as a feature, we should be fine. And the next time your project manager tells you you have no time for front-end optimization because it doesn't matter, there are many statistics all over the internet that proves he or she is wrong, actually. So grab those statistics and present them. Because by having a website that loads faster, it can translate into more revenue for the businesses. Second thing is to look for easy wins. Not everything I have shown today was super hard. Some of the things were actually low-hanging fruits, like preload for fonts, or asynchronous scripts, or some basics like cache headers. These are things that in a project of every size that should be you should be able to accomplish it within hours or even minutes. And there is really no reason not to have it. It's a thing that can only benefit the project. So just by applying this, we might have a really good progress on the performance front. Last and most important is to ship less code. We should be always thinking about that whenever we are adding something. Do we really need to have jQuery in 2017 if it adds 0.6 seconds to the loading time on slow 3G? And we can have all the same DOM manipulation functionality in like 5 lines of native JavaScript nowadays. We should always convince ourselves that the thing we are adding to our front-end project actually gives more value than it costs. If you need a full recap, the slides are already available at slides.com/adambar/mobilewebperf with all the links that I have shown you. Thank you. We have some time for questions, probably. If you have any. Sure. I don't have it.
Hello. Okay, so it looked like you did the cache headers and also the progressive web app service worker. And the service worker was way faster, I think, than doing just the cache headers. Why is that? Because it seems like for both of them, you're just telling the browser to reuse what it has locally. So why would one be so much faster?
Let me think. Well, actually, I'm not sure. Well, it might be that not everything that is actually immutable in my case was served. Yeah, exactly, because I am using the external resources like fonts from Google Fonts, like some other things from external website that I'm not controlling. So not everything can have a cache header applied by me. And in case of service worker, I am able to store things that I am not owning and that are external for me. So I think this is one reason. Is there anything more? I'm not sure.
Well, that seems like a good reason, so thank you.
Anyone? Thank you then.